Okay, we are here. This is exciting. We're going to talk about the halting problem. This is like one of my most favorite topics in this course. If I could have, dancing fireworks and stuff, that would be great. So imagine there are fireworks around here. I hope I'm not. That's supposed to look like fireworks. I suppose fireworks burst out all directions, right? This is cool. This is fun. I don't want to oversell it. I probably have already oversold it, but we're going to talk about the halting problem now, which is one of my favorite topics. It really is, of all time. So let me start by praising the work of Craig Kaplan. I'll show you this on here. This explanation is based on the fantastic work of Craig Kaplan, and I give you the URL where you can find his explanation of the halting problem. I did not love the halting problem as much as I do now before I saw Craig Kaplan's explanation of it. So if it turns out you think this is pretty cool, it is not just me you have to thank, but Craig Kaplan. Okay, so we're going to talk about the halting problem. Remember, we have been building up to this for ages. This is the point where we're going to show that there is some programs, well, that there are some programs that cannot be written, period. Nobody can write them. You can't write them. I can't write them. No one can write them, okay? And to get there, we have to start by just defining a problem. And all we're going to say is that a problem is just a yes or no question that we ask about some input. So we want to write a program, we're going to call it, it's a Boolean method, right? And here are some problems, right? So given 1 put x, is x a prime number? Or given x, y, and z, if I add x and y, multiply by y again, is that the same as z? Or if I have two inputs, maybe the first one is a Turing machine and the second one is a string. Of course, you could figure out how to input a Turing machine, right? Either we have a Turing machine object that we design, but at the lowest level, Turing machine could be specified by its instructions, which could mean that we have, a string that has a bunch of tuples in it, right? But anyway, however we make these parameters to our method, we've got a Turing machine, we've got a string, and the question is, does Q accept S? So these are just examples of problems, right? So just remember, a problem is a yes or no question, right, that we ask about input. And one more definition, we'll talk about how an algorithm is a solution to a problem if two things are true. First off, of course, it has to give us the correct answer. If it doesn't give us a correct answer, it's not a solution. And the other thing is it's guaranteed to run in a finite amount of time. It's very nice if you have a method that 50% of the time gives you an answer and the other 50% of the time ends up in an infinite loop, but most people aren't going to accept that as a solution to your problem, right? So it's only a solution if it both gives the correct answer all the time, and if it stops at some point, it's guaranteed that it will stop. Now, at this point, I need to warn you that what's probably going to happen with this lecture is the following. You are going to watch, you're going to go through these slides. Every single step, every single slide is going to make sense. You're going to be fine with it until we get to the last slide, and then you're going to say, wait a minute, how'd she get there? What happened? And you're going to go back and you're going to try and, you're going to want to go back and take another look and figure out what's going on. And that's to be expected. This is weird. There aren't, most programs can be written. It's the strange programs that require you to do a triple backflip along a Mobius strip while you're, pouring water out of your Klein jar. It's weird, okay? It is weird. This is weird. So what I want you to do is watch this video through. At any time, if something doesn't make sense, pause and make sure that particular step makes sense. But then when you get to the end, if the logical step-by-step process doesn't make sense, then just go back and watch it again. You'll get it. Okay, here's the halting problem. And we have two inputs for this problem. Remember, problems have inputs. The first input is my method, which is a Java method, right? And you can imagine, again, maybe it's an objective type method, maybe it is just a long string that has the text of your method in it, right? And then we have a second parameter, which is the param string, right? So maybe my method takes 5 parameters, and this would be a string of those 5 parameters. Maybe my method takes 27 parameters. This would be a string of those 27 parameters that could be given to my method. So given these two inputs, the question is, can you write another method? And we're going to call that method would-it-stop. And here's what would-it-stop should do. It should return false if my method would get stuck in an infinite loop when given the parameters param string. And it should return true if my method would stop running in a finite amount of time and give you an answer given this parameter string. You with me? So it's definitely a problem, right? It's a yes or no answer. Okay, we're returning true and false, not yes and no, but you're with me here, right? So we want to write the would-it-stop method. The would-it-stop method takes 2 parameters. The first parameter is of type method. The second parameter is of type string. And would-it-stop returns false if my method gets stuck in an infinite loop, and returns true if my method does complete in a finite amount of time. And of course, the question I'm going to ask you is, can we write would-it-stop? Right? Is this a method that we can write? Well, we can certainly start writing would-it-stop, right? So here's my would-it-stop method. It takes 2 parameters. The first is a method. The second is that parameter string of the parameters that we're going to pass into my method. And you know, here's an outline of the would-it-stop, right? If something really smart, of course, this is the magic part, then return true, else return false. Right? Looks good to me. So that was easy, but is it possible to fill in this part and make it work? And of course the answer is no. You knew that was coming, right? You knew for sure, given the buildup I've given to this thing, that the answer is no. And what we're going to do in the rest of this lecture is just talk about why not. Now, before we start proving this, let me point out that of course we could make the would-it-stop method work on some input, right? You know, if we say, all right, we're going to limit the kinds of methods that we can use as input, then you know, I mean, we could write would-it-stop for some methods, right? So for example, let's take a look at this method called stopper, right? Stopper takes a single string, and you know, for no apparent reason makes a new variable x, assigns it 5, it prints it, and then returns true. Great. So, you know, stopper is a method that always stops. So, I mean, you know, no matter what string I enter as a parameter to stopper, it's going to stop, right? So, you know, stopper, if the parameter is hello, it will stop, right? Stop, remember, stop just means, you know, completes in a finite amount of time, right? And by completes, I mean gives us an answer, or gives us the right or correct answer. Right? You know, if I input Rowan as a parameter to stopper, the method is going to stop. No infinite loop. It's just going to return true. And this is kind of interesting. Notice that I could turn the text of stopper, pretend this is one long line of text. It wouldn't fit on my slide. It wouldn't give me room. But if that were one long line of text, I could run my stopper method with the parameter which has the text of my stopper method, but even in this case, it's going to stop, right? It will always stop. Stopper always stops. So I could write a specific would stopper stop method, right? For this particular stopper method, and no matter what the parameters are, you just return true, right? Stopper always stops. So did you guess what was coming next? I'm sure you did. I've got this method called Loopy. Loopy gets stuck in an infinite loop, right? So as long as x is 5, so x gets initialized to 5. As long as x is 5, we update x by adding 1 and subtracting 1 to it, which means it stays as 5, and we're stuck in an infinite loop, right? So no matter what the parameter is that we pass into Loopy, we're going to loop forever, right? So if I pass in the string hello, we will loop forever. And if I pass in the string Rowan, we will loop forever. And if I pass in the string, pretend this is one long string, right, which happens to be the text of the Loopy method as the parameter, so s becomes the whole text of this method, that's fine. It's still going to loop forever. And so we could write a specialized method called would Loopy stop, right? And again, it's easy to write. You just always return false, right? Because Loopy never stops. Loopy always ends up in an infinite loop. No matter what your parameters are, Loopy will not complete with an answer in a finite amount of time. Okay, so now we are going to prove that it is impossible to write a generic would it stop method, right? One that takes any method along with parameter string and returns true if this particular method, when given this particular parameter string, would stop with an answer after a finite amount of time, and returns false if this particular method on this particular parameter string runs forever, right? Has an infinite loop, okay? And I'm trying to prove that we can't write this generic would it stop method that works for any parameters. I'm going to do a proof by contradiction, which is really fun, right? That adds to the fun of this because proof by contradiction is just a great proof technique. So what do I mean it's impossible to write this method? Didn't I just write it? And hopefully you're not saying yes, right? Because, as we both know, it's this expression in here, this condition that is going to be really hard to write. And what I'm going to prove is that we cannot fill in this condition. We just can't write anything in here. There's no way to figure it out. So the method works for arbitrary parameters, right? Where we're talking about we can't make the would it stop method perform given a pair of parameters. So let's get started with our proof that we can't write a would it stop method. We're going to start, of course I told you it's proof by contradiction, right? By assuming the opposite. So we're going to assume that it's possible to write the would it stop method. And I'm going to give you a series of steps that will eventually end up with some sort of a contradiction, at which point we'll say, well, I guess my assumption was wrong. Okay? So for starters, we're going to assume it is possible. Now, if it is possible to write the would it stop method, then I could take any old method I want and any old parameter string, and I could check it, right? So I could check would it stop on, some method with the string ABC. And I could check that same method with a different string, right? 3.14 comma 7, and would it stop would either return true if this method returns an answer in a finite amount of time, guaranteed, or false if it goes into an infinite loop. And since would it stop is a generic method, it's going to work on any method and parameter pair we put in. I don't have to just run it on some method, I could run it on another method, and I could pass in the string Mary had a little lamb as my parameter, and would it stop would give me the correct answer. And if I had a super cool method, would it stop would still work. And I could, I could put in a really long parameter string. I could put in the text of the entire U.S. Constitution, including the preamble, and all the amendments. And would it stop would give me the correct answer. It would tell me whether cool method would go into an infinite loop or whether it would stop in a finite amount of time and give me the answer. And finally, I could also run would it stop on my cool method and pass in as my parameter string the text of cool method, right? Just like I did with the specific examples, like with Loopy, when I just quoted all of the contents of Loopy, all the text of Loopy, and passed it in. I could pass cool method in with the text of cool method. I could, run it on the method foo and pass in as a parameter the text of foo. Right? These less than and greater than signs are with me here, right? These are just to say, replace this with the text of cool method, replace this with the text of the U.S. Constitution, replace this with the text of foo. But I could do this, right? I could run would it stop on a method with its own text if I wanted to. Now, running a method on the text of that method is so cool, right? If I could do that, I would want to do it all the time. And so, because I get a little bit lazy when I'm programming, I wouldn't want to always run my would it stop method and have to put in, my method and then the string version of my method, twice in a row. I might want to write a method called stops on self, right? And that just takes the method once as a parameter. And the answer it returns is it just runs would it stop on my method with the text of my method as a parameter, right? So this is just a nice little shortcut, so I don't have to type so much, right? So I could try stops on self on my cool method, and I could try stops on self on my not so cool method. I could try stops on self on Microsoft Word, all sorts of things. In particular, of course, if I run stops on self on that stopper function we talked about earlier, it would return true because stopper always stops, so it's going to stop on itself. On the other hand, stops on self for Loopy is always going to return false because it never stops on itself. Even when, Loopy never stops, right? Loopy is always in an infinite loop, no matter what the parameters are. So even if the parameters are the text of Loopy, right? So if I pass in Loopy and the text of Loopy, still going to have an infinite loop. If I pass in stopper and the text of stopper, it's always going to stop, right? And give me an answer. These are just some examples. So continuing, if I can write this method called stops on self, then I can also write a method called Bob's your uncle. And if you've never heard the phrase Bob's your uncle before, you can look it up in Wikipedia. According to Wikipedia, Bob's your uncle is an expression of unknown origin commonly used in Great Britain and Commonwealth countries. Typically, someone says it to conclude a simple set of instructions similar to the French expression et voilà. Bob's your uncle is an exclamation that is used when everything is all right and the simple means of obtaining the successful result is explained. I knew you were interested in this. That's why I'm reading you the Wikipedia entry. But it says, for example, left over right, right over left, and Bob's your uncle a reef knot, right? So whatever, Bob's your uncle. So why did I call this method Bob's your uncle? I called it Bob's your uncle for the simple reason that Craig Kaplan, my Halting Problem hero, the guy I mentioned in the second slide, called it Bob's your uncle in his proof. So I'm calling it Bob's your uncle. Thank you, Craig Kaplan. Okay, would you like to continue with the proof? Let's keep going. Though maybe I woke you up. Hopefully I woke you up because this is too exciting to fall asleep. Don't fall asleep, right? Let me give you some more fireworks. Woohoo, this is cool. So far it's cool, right? So far nothing surprising, right? Nothing up my sleeve. We're doing pretty well. Dr. K has gone a little bit goofy. It is my favorite topic. I told you that. Okay, let's keep going. So, if I can write the stops on self method, then it is possible to write Bob's your uncle. This is the full method, right? Here's how Bob's your uncle works. It takes a single method as a parameter, and if the stops on self self for that method, if I run stops on self on that method and the method stops, right? So if stops on self returns true, which says that my method, when it's run on the text of itself, if it does stop, then Bob's your uncle goes into an infinite loop. Sneaky, huh? And if I have a method that doesn't stop on itself, so for example, if I run Bob's your uncle on Loopy, well, Loopy does not stop on itself, so it'll go to else and it will just return true. So if I run, Bob's your uncle on stopper, it'll end up in an infinite loop. And if I run Bob's your uncle on Loopy, it will stop, right? By the way, quick public service announcement. If you really want to look up Bob's your uncle on Wikipedia, look it up this way. Okay, back to the lecture. In the more general case, whatever your method is, if that method stops on itself, then Bob's your uncle runs forever. And if that method runs forever when given itself as input, then Bob's your uncle will stop quickly and just return true. Okay, so let's just remind ourselves where we are. If we have a method M that stops when you run it on itself, right, then it'll return true, and so Bob's your uncle on M will run forever. On the other hand, if M does not stop on itself, right, so I run stops on self on M and it returns false, then Bob's your uncle will stop with parameter M. Okay, now everybody take a deep breath, because here's where the kind of exciting part gets started. So what happens if I run Bob's your uncle on itself? Well, there's two possibilities, right? If I run Bob's your uncle on Bob's your uncle, it might loop forever, or it might stop. Let's assume, let's just say what happens if it loops forever, and see where we go from that. Well, of course, if Bob's your uncle running on itself loops forever, then stops on self on Bob's your uncle is going to return false, right? Because it loops forever, it doesn't stop on itself. But hang on, if we have Bob's your uncle stops on self, well, we know that if stops on self returns false and stops on self Bob's your uncle returns false, then Bob's your uncle on M stops, which means that Bob's your uncle on M, which happens to be Bob's your uncle, will stop. And now we get worried because we said Bob's your uncle run on Bob's your uncle loops forever, which means that Bob's your uncle on Bob's your uncle stops, which does not look good. But you don't have to panic yet, so this is the good news, right? We assumed that Bob's your uncle running on Bob's your uncle loops forever, right? That's what we said. We said, what if Bob's your uncle on Bob's your uncle loops forever? But we didn't say for sure it does. So right now we can just still, kind of go along happy-go-lucky and say that must just be wrong. We don't have a contradiction yet as long as the other case is okay, right? We said, what if it loops forever? Well, what if it doesn't? So when we run Bob's your uncle on itself, what if it stops, right? We know it doesn't loop forever, right? So what if it stops? Then just, because how we know the stops on self method works, if Bob's your uncle on itself stops, then stops on self on Bob's your uncle will return true. And if stops on self Bob's your uncle returns true, well, if stops on self M returns true, then Bob's your uncle on M runs forever. So if stops on self on Bob's your uncle returns true, then Bob's your uncle on Bob's your uncle should loop forever. So we've got Bob's Your Uncle Run On Itself stops. Bob's Your Uncle Run On Itself loops forever. And now we start to panic because both cases don't work. Now, of course, secret behind the scenes, right? We wanted it not to work, right? We were trying to prove by contradiction. If we didn't get a contradiction, I can't write scenes and talk at the same time. If we didn't have a contradiction, you know, our proof would be hopeless. But the way we play this is, oh, let me assume it's all fine. I assume it's fine, so let's just play along. What if I run Bob's Your Uncle on itself? Oh, that one doesn't. That's fine. Don't panic. If it stops, that's fine. Don't panic. And now we're at the panic. All right? We have a contradiction, right? Both cases don't work. No matter what I do, I end up with a contradiction. Therefore, my initial assumption must be false. What was my initial assumption? My initial assumption was, let's assume that it is possible to write the would it stop method. So that's false. So I can't write would it stop. So there exists a program that is impossible to write. QED with some more fireworks. Right? You got to admit, this is cool. There is a program that is absolutely impossible to write. We can't do it. Done. You know what? I'm going to celebrate so much, I'm going to add another color into the color scheme. Let's do some green fireworks. Can you have green fireworks? And one more color. Are there orange fireworks in reality? I don't know, but you get orange fireworks as an extra special bonus.